Yes. Okay. Hello, everybody. First, let me thank organizers for organizing this meeting. Today I'm going to talk about how adopting different IMF or IGMF theory may change our physical interpretation from observational data, from globular clusters to dwarf galaxies and the spiral galaxies. Here I just focus on ultra-compact dwarf galaxies and recent observation about mass to light ratio of super spiral galaxies and compare their properties adopting invariant canonical IMF and IGMF theory. First, I briefly introduce the canonical IMF and IGMF. The IMF is the initial mass function of stars that form together in a star formation event. And so IMF give a number of stars that form from each stellar mass. Here, the salpeter IMF and Krupa IMF is compared as an example. And salpeter IMF is a single power law function, and canonical IMF or Krupa IMF is a power law function with two slopes. Alpha 1 is minus 1.3 for masses below 0.5 solar mass, and above it, the slope of mass function is minus 2.3. One of the main questions is that whether the IMF is a universal probability distribution function or it is an environment dependent function. This is an important question because chemical evolution of a stellar population, estimation of physical properties of such as mass to light ratio and baryonic mass of stellar systems, and also formation and evolution of stellar systems are strongly dependent on the shape of the IMF. Theoretically, it is expected that the IMF varies and, for example, become top-heavy for high-density and metal-poor star-forming regions. Also, the observed extragalactic data indicate a correlation between the star formation rate and the slope of the IMF. So, for active galaxies with high SFRs, more top-heavy IMF is expected. Therefore, based on this observational data, Krupa and Widener introduced integrated galactic IMF or IGMF theory for IGMF theory to formulate the Galaxy-wide IMF. The basic idea is that all stars form in an embedded clusters, embedded star clusters. And the IMF within embedded star cluster is canonic for low density, but in general form, the slope of mass function for masses above 1 solar mass, alpha 3, depends on metallicity and density. The maximum stellar mass that can form in an embedded cluster can be determined from solving these two equations together. And the embedded cluster mass function is assumed to be a single power law function where beta, the slope of this mass function, depends on star formation rate and is about 2. So the stellar mass function of a galaxy or a star cluster complex is an integration over the IMF of all these embedded clusters. You see here the result of IGMF theory, that you can compare them with the canonical IMF dashed black line, which is clear at here. These are for different star formation rate and different metallicities.
Sorry, may I interrupt you? Could you please turn off your camera?
Okay, sure.
Some technical problem here.
Okay, sure.
Thank you.
Okay, ultra-compact dwarf galaxies or UCDs are extremely compact objects with dynamical mass in the range of 10 to the 6 to 10 to the 8 solar mass, with size less than 100 parsec. So their physical properties are similar to massive globular clusters and nuclei of the galaxies. This makes them objects between globular clusters and galaxies, but their mass-to-light ratios show a deviation from mass-to-light ratio of globular clusters. Sorry. Okay, in fact, observed mass-to-light ratio of UCDs are larger than what is expected for simple stellar population, assuming canonical IMF. Okay, different formation scenarios have been proposed to explain the origin of UCDs. As Holger mentioned some of them, they could be remnant nuclei of galaxies which are tidally stripped because of external field, or they can be a supercluster which form from merging between globular clusters, or they are most massive star clusters that collapse to form UCDs. Okay, here I'm going to compare merging and monolithic collapse scenario. And to simulate UCDs population based on these two scenarios, we use the stellar population synthesis technique. So we need to first determine IMF of each of these scenarios based on these scenarios. Okay, in monolithic collapse scenario, we assume that UCDs are massive end of globular clusters distribution and whole population is formed at the same time. So monolithic scenario leads UCDs to have more top-heavy IMF. While in the merging scenario, UCDs form through merging of star clusters with different masses encounter to each other, and result a massive object with larger radius and IMF. That is calculated from integration over the IMF of all merged star clusters, same as the IGMF theory, following the IGMF theory. Okay, for stellar evolution, we use Padova database, and for dwarf stars, neutron stars, and black holes, the remnant masses is adopted from this relation, and Boston spectral library is also used. We set up a grid of models with different mass from 10 to the 5 to 10 to the 9 solar mass and different metallicities to compare mass-to-light ratio of modeled UCDs with observation. We also assume different retention fraction for remnant stars. Okay, here we compared the observed mass-to-light ratio of UCDs with SPS prediction based on the monolithic and merging scenario, assuming 10% and 100% retention fraction. In fact, from canonical IMF, invariant canonical IMF, we don't expect to have a correlation between mass and mass to light ratio of UCDs. But here, it is clear that monolithic scenario with top-heavy IMF is in better agreement with observed data. And here you see the effect of metallicity. With increasing metallicity, mass to light ratio in V band increase, but again canonical IMF could not give us the observed trend of mass to light ratio. Okay, but we know that retention fraction is not constant for UCDs with different masses. Mass dependency of retention fraction is investigated by Yerokova et al. Assuming different kick velocities that you see for low mass UCDs, retention fraction is about 10% and increase with mass of UCD to 100% for massive UCDs. But it depends on our assumption about peak velocity, of course. Okay, here you see mass to light ratio of modeled UCDs based on the monolithic scenario using mass-dependent retention. Using mass-dependent retention fraction, and with this scenario and top-heavy IMF and adopting more realistic retention fraction, we get very good agreement to observation for age of about between 7 to 10 gigayear, which is reasonable age for UCDs. Okay, in addition, we compared present-day radius of modeled UCDs with observation. For initial half-mass radius, we used Marx-Krupa relation to calculate present. For initial half-mass radius, we used Marx-Krupa relation, and to calculate present-day radius, first, we considered early expansion due to the stellar evolution. I mean, first 100 megayear that massive stars evolved. For this, we used the results of M-body simulation for top-heavy IMF by Haqi et al. And here we plotted half-mass radius at 100 megayear versus alpha 3, the slope of mass function above 1 solar mass. We find the best fitting function, and to this data, you see it here, and so using this relation, the half-mass radius of UCDs at 100 megayear are determined. You see in this here in the right hand, blue stars are the initial half-mass radius, and black ones are at 100 megayear. Gray circles are the observational data. And we also add the effect of dynamical evolution, which is shown by red triangles, using following Baumgart-Martineau relation. And as you see, dynamical evolution, which is shown by red triangles, is more important for low mass UCDs. Okay, so as a conclusion, I would say with monolithic collapse scenario and top-heavy IMF, metallicity and density dependent IMF, we can reproduce observed mass to light ratio of UCDs and also present the radius of them. Okay, here I switch to the second part, baryonic-Tully-Fisher relation. Okay, baryonic-Tully-Fisher relation relates dynamical mass at the radius where rotation curve becomes flat, okay, to the total baryonic mass of a galaxy. I mean, with total baryonic mass, I mean the stellar mass plus gas mass. Okay, recently, Ugle et al. Found that super spiral galaxies deviate from baryonic-Tully-Fisher relation. You see the blue points in this figure are recently observed super spiral galaxies. In fact, they have low baryonic mass for their high rotation velocities. The breakpoint is in baryonic mass of about 10 to the 11.5 solar mass. And okay, so to see if to see if this breakpoint is real or some observational mistake, first we should see how they measured baryonic mass of these galaxies. In fact, they assume that IMF is invariant and universal. I mean, doesn't change from star clusters to super spiral galaxies. So the IMF for very low mass galaxy is same as IMF for super spiral galaxies. Okay, and based on this assumption, they adopt constant mass to light ratio, which is about 0.6 in the measured band, 3.6 micro. So, but the question is how much the results, the measured baryonic mass, may change if nature chooses IGMF theory to create stars instead of invariant canonical IMF. Okay, here you see how mass to light ratio vary with time for galaxies with extreme masses, 10 to the 8 solar mass and 10 to the 13 solar mass, adopting canonical IMF and IGMF theory. For all modeled galaxies, a constant star formation is assumed, and you see that adopting IGMF theory for massive galaxies, we get larger mass to light ratio by a factor of 2 comparing to the canonical IMF. You see here. Okay, here in this plot you see presently mass to light ratio in V band for galaxies with different luminosities, and we compared our results adopting canonical IMF and IGMF theory, and you see the difference between these two IMF increase with increasing the mass of the galaxy. And here, okay, we have two plots. One of them is in V band, and another is you see the difference in 3.6 micron. So here, the baryonic-Tully-Fisher relation is plotted, and we assume that natural way that stars form follow the IGMF theory. So if observers assume invariant canonical IMF instead of IGMF theory with constant mass to light ratio, what they will obtain for baryonic mass of galaxies. It is shown by red circles, and you see the difference in high mass galaxies. Of course, here we assumed constant star formation rate for galaxies, but we know that the star formation rate is not constant for spiral galaxies. For example, it is already shown that for our galaxy that star formation is decreased by a factor of about 7 over 10 gigayear. So here we adopt exponentially declining star formation rate. Somehow that gives us reasonable present-day star formation rate, and you see the difference increase with if observers wrongly use invariant canonical IMF instead of IGMF theory. You see the results as green circles. So, as a conclusion, I would say, based on this observation, for mass to light ratio of super spiral galaxies, one can conclude that the baryonic-Tully-Fisher relation, which is direct prediction of Mond theory, is not correct. Why? The resulted baryonic mass depends strongly on our assumption about the IMF. So if IGMF was the true way that stars form, then baryonic-Tully-Fisher relation could be correct for large range of galaxy mass, and observed deviation from this relation is only based on wrong assumption about the IMF. So, thank you very much. Dr. Wahidiniya, do you hear me? I finished my talk.
Thank you very much, Ilham. It seems Dr. Wahidiniya is not available now. I don't know why, but so any questions? Yes. Pavel, do you have questions? Hello, Pavel. Thank you for joining us.
Maybe, can you hear me?
Yeah.
Can you hear me?
Yes.
Can you hear me? Hello?
Hello.
Yes,
Can you hear me? I'm going to ask a question.
Yes, please.
Okay. Thank you for a very nice presentation. Could you please show the baryonic Tully-Fisher relation?
Yes.
And compare that with the calculated one. This is the calculated one. And it seems that the IGI black, the relation with the black is on a linear line, while the typical IMF seems to get to lower values. Is this consistent with the observations?
If because I am not here, I could not hear you very well, but if I understand truly, actually we assume that in this plot we assume that the IGMF theory is correct. Then it should be on the Tully-Fisher relation. We assume that Tully-Fisher relation is a true relation, and the IGMF theory is the natural way that the stars form. Then both of them should give us same relation in this plot. Okay.
Right.
So, but if the IGMF theory is true, then but observers assume that canonical IMF is the mass function of the galaxies, then what they will get? They will get the green circles and deviation from the Tully-Fisher relation.
Yes.
But could you repeat your main question?
This is the observation.
I'm sorry, I couldn't hear you, so could you please write it?
Can you show the observed, please?
Okay, yes, sure.
And so deviation constant with the IMF.
Yes, sorry, I couldn't hear you very well, but I think that you mean that with adopting IGMF theory instead of canonical IMF, could we remove this deviation? Yes, of course. You see here that it is of the order of 1 dex at here, less than it, 0.5 dex, and here again we have same order of deviation.
Thank you.
You're welcome. Sorry, I couldn't hear you. I just guessed that what is your question?
That was correct. Thank you.
You're welcome.
Okay. No, do you hear me now?
Yes.
Okay, sorry. I have a problem with microphone. We have time for another question.
Can I ask you a question, Mohammed?
Yes, of course, please.
Thank you very much for this nice talk. I got a bit confused. Do you mean that in baryonic Tully-Fisher relation is found based on some wrong assumptions, or you mean that there are some outliers? I mean, some super spiral galaxies that are outliers, and for explaining the rotation curve, you have to use better models for IMF. Which one? I'm a bit confused about it.
Okay, I mean that actually we had baryonic Tully-Fisher relation for range of galaxies from baryonic mass from 10 to the 8 to 10 to the 11 solar mass, okay?
Yeah.
But recently, super spiral galaxies, which are super spiral galaxies are observed, which are rare, and it is difficult to observe them. It is difficult to find their rotation curve, okay?
Yeah.
But they are observed, and they show a deviation from Tully-Fisher relation,
Right.
okay?
And do you mean that if we use a better model for their IMF, then they will
Yes.
be consistent with baryonic?
Yes, actually, what I said is that if we, because when they want to measure the baryonic mass, they have luminosity of these objects, and they should multiply it to the mass to light ratio, okay?
Right.
But how they measure the mass to light ratio, they assume that the IMF is canonical, invariant canonical IMF, okay?
Yeah.
So the mass to light ratio is constant, is about 0.6 for all these galaxies from 10 to the 8 to 10 to the 12 solar mass, okay? Doesn't change. So, but based on the IGMF theory, mass to light ratio change with the mass of the galaxies.
Yeah.
Especially with the star formation rate of the galaxies.
Yes. Thank you.
You're welcome.
Okay, thank you for the nice lecture and the good question, of course.
Thank you very much.
Okay, we can start the next talk.